Okay, so let's continue. So, well, the third part is going to be a little bit assorted. Okay, so I try to finish one topic in 1 week, but it's kind of hard. Sometimes things slip to the next week. Let's see, like the best that we can do today. So before we continue further, like I think I would like to give a very quick summary of the course so far. Okay, like just a big picture of like what kind of algorithms we have seen so far. Okay, so summary of the course so far. Okay, now, well, so in machine learning, okay, there are, well, the note says 2 broad approaches, but there are actually 3 broad approaches to solve learning, okay, like or to do learning. Like so one is supervised learning, which is what we have been seeing so far, right? Now, there are also 2 other approaches, okay? So we have unsupervised learning, which is the idea of learning without the supervision labels, okay? We haven't done any unsupervised learning so far, but we are going to do some unsupervised learning towards the end of the course. There is also a third major category of learning approaches, which is reinforcement learning. And this course does not talk about reinforcement learning at all, okay? However, like I know several of you are doing my reinforcement learning course, which is happening in parallel to this course. If not, you can do it next year, okay? But majority of this course is focused on supervised learning. Now, in the case of supervised learning, like there are 2 major problems. So one is regression, right? And the other one is classification. Okay. Now, in regression, again, you can do linear regression or non-linear regression by using basis functions, right? There are other approaches, we haven't seen them. Like I'm just trying to give a summary of what we have seen so far. Okay, so we have seen linear regression, we have seen how to do non-linear regression using using basis functions, right? So now, I want to kind of tag all the approaches that we have seen so far by saying whether it is a linear or non-linear model, and whether it is a linear decision boundary or non-linear decision boundary. So this is really a quiz for your understanding. So linear regression, what kind of model it is? Is it linear or non-linear? Linear model. What about the decision boundary? Linear. Okay. Now non-linear regression using basis functions. Is it a linear model or non-linear model? Is it a linear? It's a linear model, right? Like it is still linear with respect to the parameters. But what about the decision boundary? Non-linear. Okay. Now let's go to classification. In the case of classification, there are discriminant-based approaches, discriminative approaches, okay, and generative approaches. Okay. Now, can somebody tell me whether, like, which class of approaches would k nearest neighbor belong to? So which class would k nearest neighbor belong to? Sorry? Discriminative. Why?
Because we directly just assign the class of data without any.
Because you can compute P of y given x, which is basically the average of the classes near you, right? Like, so it's a discriminative model. Okay, but in the case of discriminant-based model, we have only seen indicator regression so far, right? This is going, discriminant-based approaches is our next topic. But so far we have seen indicator regression, which is basically this idea of using indicator variables and then doing linear regression on the top, right? Now, this is a linear model with linear decision boundary, okay? Now, in the case of discriminative models, like we have seen logistic regression today, and we have seen k nearest neighbor before. right? Now, logistic regression, is it a linear model or a non-linear model? Non-linear model. Is it a linear decision boundary or a non-linear decision boundary? Linear decision boundary. So we have a name for models which are non-linear with linear decision boundary. What are they? Generalized linear models, right? Like they are still generalized linear models. However, KNNs are not generalized linear models. KNNs have non-linear, they are non-linear model because they can do any distributions, and they also have non-linear decision boundary. Okay, when you have NN, it is a pure non-linear model. Now, in the case of generative models, right, like we have seen GDA, we have seen QDA, and we have seen Gaussian naive Bayes, right? And we have seen diagonal GDA. Well, I don't have space here. So let me put discrete naive Bayes here. Discrete naive Bayes. These are the generative models we have seen so far. Now, GDA, what kind of model it is? Is it LL or NN or NL?
Non-linear, linear,
It's a generalized linear model, right? It has non-linear. It's a non-linear model with linear decision boundary. What about QDA?
non-linear,
NN, okay. What about Gaussian naive Bayes? Huh? NN, because it is just a Gaussian, like it's just a naive Bayes description on the top of QDA, okay. What about diagonal GDA? NL, because it is just GDA with diagonal assumption, right? Now, what about discrete naive Bayes? Discrete naive Bayes is also a generalized linear model. Is that clear? So this gives you a summary of things that we have seen so far, okay, in one picture. But we are going to see some more linear and nonlinear, like generalized linear models, and eventually like pure nonlinear models in few weeks. Is that clear? Okay. Now I also want to cover another topic which we failed to cover which I failed to cover last week, which is about evaluation metrics for classification. Okay. Now, in the case of regression, the evaluation metric is pretty simple. It is RMS, right? Now, so far, we have seen only one evaluation metric for classification, which is accuracy, right? Like, so we have seen accuracy, which is basically the number of correct answers divided by the total number of answers, right? Like, so now let's consider a two-class problem. Okay, let's say I have two classes, positive and negative. Okay, now accuracy is computed as number of correctly classified instances, okay, multiplied by the total number of instances. If I have 100 test points, 80 of them are correctly classified, my accuracy is 80%, right? Now, the first question is this a good metric for all the tasks? Can we get some answer from this side?
Depends.
Depends. Why?
It depends on the class distribution. If you have minority classes, no, it's not.
Okay. Well, by the way, people in the Zoom, like I am checking the chat. So for all the questions, you can asynchronously answer here. Okay. So it depends, right? Like, so sometimes when you have class imbalance, it could be a useless metrics. Let me give you the same old example. Like, let's take cancer prediction. Okay. Now, let's say I have a data set of 10,000 patients. Now, it might be the case that 9,900 patients had no cancer and 100 patients had cancer. Okay, now this situation is getting worse every year. But for now, let us just assume that, okay, I messed up my notes. Okay, so let us just assume that there are 9,900 no cancer patients and like 100 cancer patients. Okay, now I'm going to construct this really dumb classifier. You give whatever x, this classifier will always say no. Okay. Now this classifier is going to have 99% accuracy. But this is a totally useless classifier. I cannot deploy this classifier in hospitals, right? Like, why? Because it is completely against, or like it completely misses the point for the classifier in the first place. The point for the classifier is to detect cancer patients, right? Accuracy for no cancer versus cancer doesn't matter here, right? Like, so now this mismatch happens because not every error has the same cost. Okay, when you have a 0-1 loss, maybe this is okay. Okay, but even in 0-1 loss, like when there's class imbalance, this is not okay. Okay, but there are a lot of examples like cancer that the loss matrix is actually very different. Like for example, there are two types of errors that the system can make in this cancer application, right? There are two types of error. Okay, so the first error is you classify patients without cancer as yes. Okay, now the second type of error is classify patients with cancer as no. Okay, now I think we all agree that the second error is more dangerous than the first error, right? Of course, you should not make the first error too. Like it has some cost. The cost is, let's say the doctor says you have cancer. Now, often like they don't finish it there. Like, so they want to take more precise tests later. Now, these tests might be costly, like $2,000 or $3,000 or $10,000. Okay, you do these costly tests for next couple of weeks. Then these highly precise tests tell you that okay, you don't have cancer. Then you're good, right? So now you had this 2 weeks of mental pressure, like or little bit of like extra like issues in your head, right? Like, and also of course the cost. But then you can rectify this error, right? Like on the other hand, let's say you really had cancer. But I don't want to give you as an example. Let's say someone really had cancer, and the doctors using a machine learning system, and the system says the patient doesn't have cancer. Now the patient goes home, never does a test again. In 2 years, they could die, right? So the second error is way more costlier than the first error, okay? Which means we should start thinking about different types of error when we are assessing how good is a system, okay? To do that, we are going to use the concept of confusion matrix. Okay, so what is a confusion matrix? I'm going to do all this discussion with 2 classes. Okay, you can generalize it for many classes, but I will leave that as an exercise. Okay, so we will not discuss K-class evaluation metrics here. However, in your third assignment, you will be implementing or using K-class evaluation metrics. So you have to think about how to extend these to K-classes. Okay, now let's consider this matrix where the rows, the columns are true values, and the rows are predictions. Okay, so positive, negative, positive, negative. Okay, now this first entry tells us out of all the examples, okay, how many of the examples are first of all positive, and my model also thinks it is positive. Okay, my model says something is positive, but in this case it is truly positive. Okay, so we're going to call this as true positive. Okay, is that clear? Now, what about this entry, right? Like this entry is what my model thinks is positive, but it is actually negative, right? So my model falsely thinks that this is positive. So this is an error, and this error is called false positive. Okay. Similarly, when things are negative and model thinks it is negative, it is true negative. And when things are positive and my model thinks falsely that they are negative, it's called false negative. Is that clear? Now, can we go back to the cancer example? Can someone tell me which error is false positive, which error is false negative. First one is second one is obviously false negative. All right, so now for this particular application, so it so happens that false negatives are more costlier, so you should not make a lot of false negatives. Okay, now let us look at some example confusion matrices. Okay, so now let's say I have 100 examples, out of which 60 are positive and 40 are negative. Okay, here is one example matrix. Like I have 40, 10, 20, 30. So now you can see that the column sums up to 60 for positive and 40 for negative. Okay, my model makes correct exam. Like if you look at the accuracy of the system, what is the accuracy of the system?
70%.
How much?
70%.
Okay, so why are people in Zoom not answering? So what is the accuracy of the system? Can you answer in Zoom chat? Okay, I want all of you to answer, not just Charles. Well, this is the advantage of joining remotely. You can actually answer all the questions. Like while people here, obviously, it's not like everyone is interested in answering all the questions. That's another issue, but you can answer all the questions in chat. So please do that. Okay, so it's 60 and 40, right? Like so now out of this 70% is accurate. The model is accurate 70%. Right? Now this is the mistake. This is a mistake, right? Now can someone tell me what would be an ideal confusion matrix? Sorry? 60, 0, 0, 40. Right? Now, first of all, why do I call this as confusion matrix? Because this matrix tells us how confused is our model. Like, so what are the confusions it is making? Like, for example, if I have something like 30, 30, 40, 30, it just tells that my model is like really confused between these two classes. It doesn't have a good idea. Okay. Now, by using this confusion matrix, I can derive several metrics depending on what I care about. Okay. But we will just see two of them. Okay. So the first metric, well, first of all, this is the matrix. True positive, false positive, true negative, false, true negative, false negative, right? This is my matrix, right? Now, the first metric that is sometimes useful is the idea of precision. Okay, so I'll first define the metric, then I'll tell you like what is the intuition. So precision is defined by true positive divided by true positive plus false positive. Okay, now this is my model's positive, negative, positive, negative. This is my model's prediction, right? Now the denominator here is this. Okay, now what does precision mean, right? Like precision means that out of all the positive examples that out of all the predictions that my model makes, which are positive, how many of them are really positive, right? So, or in other words, how precise is my model when it says something is positive? For example, let's say my model says positive for 100 examples, and out of them, only 20 are really positive, true positive. Then my model has a really bad precision. Is that clear? So that is precision. So there is another metric which is recall. The idea of recall is TP by TP plus false negative. Okay, or in other words, this is used for recall. Now you can see recall serves a different purpose. Recall tells us out of all the true positive examples, how many of them can my model accurately predict to be positive? Okay, if the data set had 100 positive examples, can my model make correct predictions for all the 100 positive examples, or what fraction? Okay, so that is recall. In some sense, like you're recalling from the data, like so can the model recall all the positive examples, right? Now, depending on like what is your situation, like one is more important than another. Okay, now can someone tell me when is precision more important? an application where precision is more important. Yeah. No, I'm asking for a practical application. Yeah.
You can say the handwritten test.
Handwritten. Okay, why is precision more important than recall there? Yeah, you.
Well, even the cancer example, you don't want to be providing any false positives.
Okay, so what is more important in cancer, precision or recall?
Recall.
Yeah.
Recall, right? Like so in cancer, like recall is more important. Like so you don't want to miss any of the patient who has cancer, yeah?
It's a videos that's for children. So you want to have a
Okay, that is actually a very good example. So that's not in my notes. Okay, it's a good example. The example is like, let's say you want to decide whether to show a video to children, right? So now it's kind of okay if you don't show the appropriate video than showing an inappropriate video, right? So precision is more important. Like the example that I have in my notes is like face password in your iPhone maybe. When you have face password, like you show your face for password, right? Sometimes it is okay if you get locked out, okay? You can always type in the password then. But it is not okay for that system to let someone else's face to be recognized as a correct login, right? Like so that's another example where precision is very important. Of course, you can think of a lot of examples, but let's move to recall. So when is recall more important? We have already seen cancer. Any other example?
Doesn't recall more important also applies in the example you mentioned, where even though you see all the videos, you wouldn't like some videos to. It's like you would rather limit the amount.
Oh, it depends on what is your goal. Oh, first of all, when I say when is precision more important or when is recall more important, it doesn't mean the other one is not important. Okay, so let's take cancer prediction. Like a very good recall system is one which says everyone has cancer. Now, will you use that system? No, right? So there is a trade-off between precision and recall. Okay, so you can easily get 100% precision with 0 recall, and 100% recall with 0 precision. Okay, but that is not our goal. Like so you always need both. But my question is about, like, for example, like which is more important in a task, right? Like so often it is going to be difficult for you to satisfy both. So can you give me another recall example? Anyone from chat? So I don't know if the light is this lie detector answer for recall or precision.
Dangerous passengers that would get in
Dangerous passenger. Okay, now we are getting into ethical issues. Can you explain more?
Let's say, so you would have a video camera that would identify if a person would be violent or not. You would need to have a better recall.
Okay.
Like identify that person is violent, then have some person that.
It's a controversial application, but it is a correct situation for recall being important. Yeah.
Safety in building something?
Sorry?
Safety in building?
Yeah.
Or any engineering stuff?
Yeah. So fire alarms, right? Like so, like you don't want to miss a real fire. But at the same time, you don't want an alarm which goes off for every single incident, right? Like, okay. I think there are a lot of other examples. Like, I will leave it to you guys to think. Now, as I mentioned, there are situations where both are important, right? Like, it is not like one is the most important. Okay, so you need both all the time. So there is actually another metric which captures the importance of both, which is the idea of F1 measure. Okay. Now, F1 measure is defined as the harmonic mean of precision and recall. So it's 2PR by P plus R. Where P is precision and R is recall. Okay. Now, this just means that you need to, if you have high F1 measure, it means you have both good precision and good recall. So for example, even in cancer detection or fire alarm detection, right? Like you should improve F1 measure because the other side is also equally important. Like not equally, but like it's also important. Let's put it that way. Is that clear? So okay. Now, as I mentioned, like I will leave it to you as an exercise to think about how to generalize confusion matrix, precision, recall, F1 measure when you have more than 2 classes. Well, of course, there are a lot of resources available online, like if you want to see the answer, but I will encourage you to think about it by yourself and then like see how people normally implement it. Okay. Any questions so far? Any questions in the chat?
I want to calculate the accuracy of the classifier. So if it is 2 class, for example, we have positive class and negative class. Then we calculate the accuracy of the positive class. That's the accuracy of negative class also. But when we have multi-class, like for example, the numbers, digits. So accuracy is the mean of the total class. Like for every class, then we have to see the mean.
Okay, I don't want us to get into the discussion.
Okay.
Okay. So I think we'll stop our discussion on evaluation methods here. Okay. So I really try to not jump to a new topic, but like we have to do it because the next class of approach is a bit longer. So if we start now, we can finish it next week. So we are going to talk about discriminant-based models. Okay, so now this is where like we are going to use the ideas of the geometrical surface of the decision surface that we have seen so far, okay, and develop more complex discriminant-based approaches instead of just simple linear regression, okay. So specifically, we are going to focus on separating hyperplane methods. Okay, this is basically a class of linear algorithms, okay, where the idea is to learn a linear decision boundary. In 2D, it's a line. In 3D, it's a plane. In 4D tasks, it's a hyperplane, right? Like so, you learn the hyperplane which separates the 2 classes as well as possible. Is that clear? Now here is an example of such hyperplane. So this is a simple 2-class problem, like a bunch of greens and bunch of reds. I want to classify, like given a new data point, right? Like so, now the yellow line that you are seeing is basically the least square solution, okay? And it so happens that for this particular example, the GDA solution is also the same line. Is that clear? Now, you can see that this line makes some mistake. So what is the mistake? So there is one green point which is in the left side, while it should not be, right? However, I'm also giving you 2 blue lines here, which are 2 separating hyperplanes with 0 error. Okay. Now, so here is the task for this week and next week. Okay. The task is, given this data set, how do I find this separating hyperplane with 0 error? Is that clear? Now, we'll start with a simple algorithm and go for more and more complex algorithms. Okay. So for today, we are going to start with the simplest possible separating hyperplane method, which is the idea of Perceptron algorithm. Okay, so this was invented by Rosenblatt in 1958. It has a lot of significance because this is probably the earliest machine learning algorithm. Like so, there is actually a very nice piece of newspaper article from 1958, like which you can find online. So it shows like how people were like having a lot of hype for AI and machine learning, even in 1958 when there was no good computer. Okay, so the newspaper article would basically says that Perceptron can read, Perceptron can make decisions, Perceptron can take complex, like make complex predictions, it can recognize speech, blah, blah, blah. Okay, so like However, we will see today that perceptron is really a simple line classifying algorithm. Okay, so I would recommend you to go read that newspaper article. Like you should be able to find it online. Okay, so now what is a perceptron algorithm? It is not going to be very different from logistic regression. It's actually a very simple algorithm. Like, so the algorithm is just one line equation. So y of x is equal to f of w transpose x. Now, in the case of logistic regression, it was sigmoid of w transpose x, right? So the sigmoid gave you the class probabilities. But now we are in the space of discriminant-based model, so we don't care about probabilities. So I just need any function which gives me the class value. Okay. Again, the bias is included inside, so it's supposed to be w transpose x plus w0. I have removed the w0 here. Okay. Now, what is this f function, right? Like, so now the f function we are going to use is actually a simple step function. Okay. So f of a is equal to plus 1 if a is greater than or equal to 0, and minus 1 if a is less than 0. So we are considering a two-class problem where the two classes are plus 1 and minus 1. Is that clear? Now we have the model. So what is the next step? So what are the parameters of this model, first of all? What are the parameters of this model? W, what? No, activation function is not a parameter. Step function is not a parameter, like just W, right? So W, okay. So now once I have the model, what is the next step?
The plus one.
Error function. We need some error function to minimize. Once you have the error function, then you either solve closed form or you compute gradients and do gradient descent. Now we can also do Newton-Raphson, right? Like, so a new algorithm. So you do whatever you want to do to find the parameters, right? So first of all, we need error function. Okay. We're going to see a different error function now. Okay. So the error function that we are going to see today is number of misclassified errors. Okay. Or in other words, it's kind of a 0-1 error function. Okay. So like out of the entire data set, the count of wrong examples, like wrong predictions, that is my error. I want to minimize this count as much as possible. Is that clear? Now, this is an interesting error function, like because, well, it's very different from the maximum likelihood or least squares that we have seen so far, right? Like, so here I say this is count based. It says, oh, I have this count of wrong examples. I want to minimize this count of wrong examples. First of all, it is not very clear how we are going to minimize this count. Is it possible to take gradients and so on, right? Like, so now this error function is actually a piecewise constant function of W. Okay, so why do I say it's piecewise constant? Because let's say I have a bunch of cross and a bunch of circle. Okay, now let's say this is my W vector, like this is a hyperplane. Now you can see that it has error of 50%, right? So roughly half of the things are wrongly classified. Well, exactly half of the things. Now I want to move this little bit. Okay, so now let's say I move it like this. Sorry. Now did the error change? No, right? So then I move it like this. Error doesn't change, right? However, when I slightly move it like this, then the error changed. Now the count reduced or increased. Is it reduced or increased? I think it should reduce. Okay, the count reduced, I guess, I hope. So then for quite some time, it's going to be same. It's going to be same until I go here. Then it's going to be same until I go here, right? So finally, the error goes to 0. So you can see that it is piecewise constant in the sense in one region when there is no crossing over examples, it is always constant. When you cross, the error changes, right? Now, this is a problem because now you cannot compute gradients easily. If you compute gradient with respect to this constant function, what would it be? What? No, it's just 0. It's a constant, right? Like, so you'll have 0 gradient throughout until this one place where you do a little bit change, which means you get a gradient. You get like small gradient, right? So you have sparse gradients. Like you have gradient only when things change, which means you cannot directly apply gradient descent here. Like we need to do something different. Okay, so that is what we are going to do now. So first, let us try to formalize this error function into a mathematical equation. Okay, so we're going to call this error function as perceptron error criteria. Okay, so this is the criteria. So we want some W. We want some W such that if x of n is in class C1, okay, then I want W transpose x of n to be greater than 0, so that I say +1. Okay. Similarly, if x of n is in class C2, then I want W transpose x of n to be less than 0, right? So that it is class -1. Okay. Now, this is like 2 if conditions. I want one equation so that I can compute gradient or do whatever I want to do with it, right? Like so now, just like how we combined positive and negative examples in Bernoulli distribution or porosity regression, like so there is a compact notation for this. The compact notation is this, like so. For any x, okay, we want W transpose x of n, p of n to be greater than 0. Is that correct? Yes or no? Like for example, if t of n is positive, okay, then I want W transpose x to be positive as well. So positive multiplied by positive, so it should be greater than 0. When t of n is negative, the only way for this to become greater than 0 is when W transpose x is negative, right? So both conditions are satisfied in one equation. Is that clear? Now, the error function for perceptron is going to be something like this. It's minus summation over n belonging to m, W transpose x of n, p of n. So is that clear? So where this m is basically set of all misclassified patterns. Okay, now this is my error criterion. Now, what does this error criterion mean? Like so, like I want this number to be maximized, which means I want the minus of that to be minimized. I want the minus of that to be minimized only for wrong examples. If something is correctly classified, that is not counted in the error. Okay, this is actually very different from the usual loss functions that we have seen so far. If you think about it, all the usual loss functions have summation n is equal to 1 to capital N, right? However, perceptron's error function just considers misclassified examples. Is that clear? Any questions? Okay, now let us just take one particular example which is wrongly classified. Okay, now that for that particular example, I want to minimize minus W transpose x of n, p of n. Right? Is that right? Now this is a linear function of W. Right? Now I can actually, it's kind of piecewise linear in the sense this is going to change once in a while. Like, so whenever there is a jump, this is going to change, right? So you're going to get 0 gradient almost everywhere, but then at some point you're going to get some gradient, right? So you can actually apply stochastic gradient descent here. So this is how my weight is going to look like. So W new is going to be W old minus eta times the gradient. Okay. Now just for one example, this is stochastic gradient descent. So just for one example, it is going to be W old minus eta times. So what would happen if you differentiate this? with respect to W? What? You get minus x and t n, right? So minus into minus is plus, plus x of n, t of n. Is it clear? So W new is equal to W old plus eta of x of n, t of n. Okay. Now, we are talking about hyperplanes here. So the magnitude, like y of x is unchanged even if you multiply w by a constant, right? So the magnitude of w doesn't matter, right? So which means for once we can actually ignore the step size eta or alpha. I can just set eta is equal to 1. Okay, because the magnitude doesn't matter. Magnitude is not going to affect my decision. Okay, so my perceptron update rule is going to look something like this: W new is equal to W old plus x of n, t of n. Is that clear? Now I'm going to do this update only when something goes wrong. Okay, so here is the final algorithm. So perceptron algorithm. This is probably one of the simplest algorithm that you will see in this course. So first you initialize W randomly. Okay, then you repeat until all data points are correctly classified. I'm going to repeat this again and again. Okay, now for each data point x and tn, okay, if y of xn is equal to tn, it means it is correctly classified. Then you do nothing. Okay, else you will update w is equal to w plus x of n. End of for, end of repeat. Is that clear? It's a very simple algorithm. Like you go through all the examples one over another. You see if it is correct, like correct. If it is correct, you don't do anything. If it is not correct, you do the perceptron update. Okay. So there is a small subtlety here. Like the subtlety is you're doing stochastic gradient descent. You're doing one after another, right? So now when you correct the correct mistake for one data point, you might introduce a new mistake for the previous data point. So the total loss is not going to be monotonically decreasing like you have seen in gradient descent. In gradient descent, you see that the loss goes almost smoothly, right? Like in this case, like there should be some bumps because correcting one might make cancellations for others and so on, right? Like so this is not guaranteed to reduce at every step. Okay, so it's going to increase, decrease, but eventually it might converge. Okay, now the question is, would it converge? Right, like so it so happens that for linearly separable problems, this perceptron algorithm will converge. Okay, so that is guaranteed by perceptron convergence theorem. So we are not going to prove the theorem in class. The theorem basically says that if the data set is linearly separable, then the perceptron algorithm is guaranteed to find an exact solution in finite number of steps. Okay. However, if the data is not linearly separable, then there is no guarantee for convergence. So we're going to talk about how to deal with it in the next lecture. But before that, I just want to show an example before we wrap up. Okay. So in this case, you see that the black arrow points towards the red flags. Okay. So currently, I'm considering this particular example. So this is a red example, so it should come to the bottom, right? So it's misclassified, which means I have to move my line a little bit towards that. So the line moves here. Now after that, I'm considering this particular example. It is again misclassified, which means I have to move my line again a little bit. So I move it here, and then finally the algorithm converges. Is that clear? So I think we will stop here. So, but next week, we are going to talk about how to extend this algorithm when you have complex problems and the data is not linearly separable anymore. Okay, so yeah. we will talk. Yeah, so we will see that tomorrow. So next week. Okay, I think that is the end of today. As usual, this is my office hour, so please come talk to me if you have any questions. And we will move towards my office, like if somebody else comes. I think people are waiting, so probably we should move. If you have any questions,